Hello students, welcome to Dr. Shorab sir classes. So in this video we are solving this UPSC 2021 maths optional paper. Okay. So in the previous video we have solved up to this question 3, so it's a paper 2. So it's in this video we will solve the question 4a and 4b. So let's start with the first question. So it is telling that show that there are infinitely many subgroups of the additive group Q of rational numbers. Okay, so what to do? So now let us take that Q, the additive group, be P by epsilon, where, or we can say that P by Q, where PQ belongs to I, okay, and Q is not equal to 0. Let us take this. So be a group, okay. Now let us take that H, be mod of this A by B. So therefore A by B belongs to Q and A comma B belongs to I, right, where B is not equal to 0, and this be a cyclic group. Okay. This be a cyclic group, and this be a cyclic subgroup of Q, of this additive group, right. Now clearly you can see that H, okay, this is equal to this A by B, which is equal to A by B X, where X also belongs to the Q, right. So it is an infinite cyclic subgroup of Q, right. So we know that any infinite cyclic subgroup is isomorphic to the additive group. So here we can write this, that any infinite cyclic subgroup is isomorphic to the additive group of all integers, right. So clearly here we can say that Z is equal to, is equivalent to the Z is equivalent to H, and also you can write it as H is equivalent to Z, right. So here H is, we know that A by B, right. So Z has infinitely many subgroups. Since Z has many infinitely subgroups, it has also infinitely many, H will also have this infinitely many subgroups, okay. So an additive group, so the main answer, we can write this, we will write in this way. So any additive group so this is additive group, that is Q, of rational numbers has infinitely many subgroups, okay. So this solves the question for the 4a, 4 part A, okay. So next we will solve the question 4b. Let's move to the next question. So question 4b, it is saying that using contour integration, you have to evaluate this integral minus infinity to infinity sin x by dx, x into x square plus a square, where a is greater than or equal to 0. Consider the integral c e to the power I z by z square a square of dz. Okay, integral c f z dz taken around the contour c, consisting of 1. The real axis from P to R, okay, a large semicircle, number 2, a large semicircle okay, in the upper half plane, given by this mod z is equal to R. So point number 3, real axis from minus R to minus P, and point number 4 is that a small semicircle Y named as Y, given by this mod z is equal to P. Okay, so how the diagram will be, so here I am, so it will be like this. Okay, so this is going to be Y. Okay, so this is minus R, this is R. Okay, now here it is a small semicircle, as you can see, this is Y, and this is the large semicircle on the upper plane, given by capital tau. Yeah, okay, so that is the figure we have, the representative figure. Now since this fz has simple poles at z equal to 0, okay, and plus minus ai, of which only z equal to ai lies on C. Okay, so the residue of f at z equal to ai, it will be this limit z tends to ai, z minus ai fz. So this is will be, okay, this is it will be limit z tends to ai e to the power iz by z multiplied by z plus ai. Okay, so this is going to be e to the power minus a by minus 2 a square. By residue theorem we will get okay, by residue theorem we get this integral c fz dz, this equal to integral mu to r, okay, fz dz plus capital tau fz dz plus of integral minus r to minus p. It will be fx dx plus the last one, it will be y. A semicircle is given, this fz dz. Okay, now if you put this, it will be minus 2. Now this equal to will be 2 pi I e to the power minus a by minus 2a square, which is equal to minus of pi I by a square e to the power minus a. Let us take this as equation 1. So by Jordan's lemma, okay, so just hold on, this Jordan's, okay, that is by Jordan's lemma, this is gonna be limit r tends to infinity integral mod this tau f of z dz is gonna be 0, right? Now since we have this limit z tends to 0, z of is gonna be fz, so we will have limit z tends to 0 e to the power iz by z square plus a square equal to, it is 1 by a square, z equal to 0. So hence the integral y, okay, fz dz, this is equal to, so this will equal to I by a square, okay, 0 minus pi. So it is minus pi I by a square. Okay, so hence as p equal to 0, this p tends to 0, okay, as p tends to 0 and r tends to infinity, so from 1 we will get integral 0 to infinity f of x dx plus minus infinity to 0 f of x dx minus of pi I square by a square, minus pi I by a square is equal to minus of pi I a square e to the power minus a, right? So or we can write this as integral minus infinity to plus infinity e to the power ix by x into a square plus x square dx, right? So this is equal to pi I by a square 1 minus e to the power minus a. So equating the imaginary parts, so from here we can get the this answer of our this integral. So here is equating imaginary parts, we get this integral of minus infinity to plus infinity sine x dx by x multiplied by x square plus a square, it will be pi by a square okay, so it will be pi by a square 1 minus e to the power minus a, right? So that will be the answer for our question number, this is 4b. Okay, so I have evaluated the integral, so this is gonna be pi by a square 1 minus e to the power minus a, right? So this about this question 4a and 4b. So in the next we will solve the last part of this, that is the question number 4c. So see you in the next video.